All right, everybody. Like I said, I was going to give make a video detailing this worksheet. This is our buffers worksheet. Um, and in class, we made it through 5. What I wanted to do is take over and complete questions number 6 and 7, because arguably those are some of the more challenging ones. What I'm going to do, however, before I do that, is I'm going to go back and fill in some of the blanks on some questions here. So the first one that I'm going to work with is question number 3. Um, what is the Henderson-Hasselbalch equation? pH equals pKa plus log of the concentration of the deprotonated form over our concentrated form. Okay, the next question that I wanted to work on was how many moles of acetic acid is needed to make 1 liter of a 10 millimolar buffer? Okay, so we know that our volume is 1 liter, and our concentration, our desired concentration, is 10 millimole per liter. And so that's going to give me 10 millimole, which is the same as 0.01 mole. Okay, now I'm going to use that information later on. 0.01 moles of, I'll label it as AA, or acetic acid. Okay, now I'm going to skip 4 because we talked about that. That's more of a conceptual, kind of theoretical type of question. Question number 6, on the other hand, is one where we actually have to do a calculation. I'm going to adjust something on my computer here. Hopefully, is that gonna? No, it's not going to. The question asks, what is the ratio of sodium acetate to acetic acid for the buffer with a pH of 4.0? And in order to answer this question, we're going to say pH is equal to pKa plus log of A minus over HA. So this A minus is our sodium acetate. And HA is our acetic acid. Okay. Now, from previous question, we know that our pKa is 4.8. So the pKa of acetic acid is 4.8. So what I'm going to do is I'm going to use that information as well as this pH information to fill in the Henderson-Hasselbalch equation. And I'm going to write pH of 4.0 equals 4.8 plus log of the concentration of the deprotonated form divided by concentration of the protonated form. And whenever I subtract 4.8 from each side, so now that I have that formula, I'm going to be able to come up with a new equation, or, well, negative 0.8 is equal to log of the concentration of A minus over HA. So now that I have a log on one side, I need to undo that, or basically get rid of that. So what I'm going to do is I'm going to say log, or 10 to the log A to the HA. If I do that to the right-hand side of the equation, I got to do it to the left-hand side of the equation. And what that's going to give me is 10 to the negative 0.8 equals A minus over HA, which 10 to the, I had a calculator around here. I got one on my computer. And what that gives me is 0.158 equals concentration of my deprotonated form over my protonated form. Okay, so question number 6 just asks me for a ratio. What is the ratio of the concentration of A to HA? Okay, so what that is telling me is that, well, I'm or it kind of confirms to me what I already know, and that is that the protonated form, the acetic acid, is favored over, or more so, than the sodium acetate. Now, question number 7 asks us to kind of take the next step. And question number 7 says, how many milliliters of 5 molar sodium hydroxide is added to the 1 liter of our 10 millimolar acetic acid solution to reach the final pH? Okay, now we have to use that ratio, that 0.158. But what we're going to do with that is use it to figure out how much of each component is present. So the first thing that I want to do is I want to write out 0.158 is equal to deprotonated over protonated. I want to rearrange this, and so that I can put this all in terms of A minus, my deprotonated form. And I can do that simply by multiplying each side by HA, or the concentration of HA. And so whenever I do that, I end up with 0.158 times the concentration of HA is equal to the concentration of A minus. Now our question is asking how many milliliters of that 5 molar sodium hydroxide is added to our acetic acid solution. What this tells me is this gives me a little bit of information about my amount of A minus and my amount of HA. So now that we have this number right here, what we're trying to figure out is we want to figure out the equivalence of NaOH to add, because as soon as we find out the equivalence, then we can figure out the number of moles of NaOH needed. And once we have the number of moles of NaOH needed, then we can have the volume. So what we're going to do is we are going to look at this kind of as, or our question is really going to be, what amount of HA needs to be deprotonated and then when we look at that, then we can say, well, the amount of HA that needs to be deprotonated is the same as the ratio of our deprotonated, our sodium acetate, the concentration of that, divided by the total amount of acetate present in the solution, both in the form of sodium acetate plus our HA. So effectively, what we want to do is use this definition right here. The concentration of A minus is equal to 0.158 times the concentration of HA. We're going to use this equation right here as a definition for A minus. We can figure out, or we can place A minus in this equation, and therefore, once we do that, we can say 0.158. We can rewrite this equation divided by, plus HA. Okay. So when we have this formula or this equation right here, what we can then do is find a common variable. That common variable is our HA. We can cross that out. So we can rewrite this equation. We can cross this out and basically make any place where there's an HA equal to 1. So that gives us 0.158 times 1 divided by 0.158 times 1 plus 1, which gives us ultimately 0.158 divided by 1.158. When we have that 1.158, or 0.158 divided by 1.58, that is equal to 0.136. Okay, so that 0.136 is the equivalence of sodium hydroxide that we needed to add. So that's what we were just solving for by looking at the fraction of our HA and A minus to one another. Okay, now how do we use that information? Once we have this 0.136, well, then what we can do is take that and say, well, we needed to add 0.136, and we can multiply that by, scroll back up to the top here. Where did it go? The 0.001 moles of our acetic acid. So 0.01. So what that gives us is we added 0.00136 moles of NaOH to this mixture. Now, we have a solution. We have a 5 molar solution, and we want to figure out the volume. So we know that concentration times volume equals moles. We have moles. We have concentration. We need volume. So we're going to rearrange this so that it reads number of moles, 0.00136 divided by 5 is our volume. 0.00136 divided by 5 equals 0.00272 liters, which converted into milliliters is 2.72 milliliters of NaOH. Okay, so just to recap, I would say that the most direct portion of this particular problem was working with the Henderson-Hasselbalch equation. You had your pH, you had your pKa, navigating that log and using the anti-log function in your calculator gave you that ratio of your two concentrations. Now, what's important to think about there is when you relate two values, a ratio, it's a unitless number because we're comparing two concentrations. Now, what we wanted to do there was we took those concentrations, or that ratio, and we needed to figure out how does that relate to our protonated and our deprotonated species. And when we think about our protonated form compared to our deprotonated form, we had to look at this equation right here, where we looked at, well, when we add a certain amount of sodium hydroxide, we will have a concentration of the deprotonated form of a molecule, or of that molecule, that we will have that sodium acetate. Okay, so that's our free sodium acetate in there. But what we want to do, or what we need to do then, is think about Well, does that account for all of the acetate in that solution? It doesn't. We have sodium acetate, which I'm going to label as NaAC. We have a concentration of sodium acetate, but then we also have acetate that is still protonated, which is our acetic acid. So what we wanted to do was think about and put our or look at our ratio in the context of how much total acetate is in that system. So that's where we came up with this concentration of A over concentration of A plus HA. So the deprotonated form over deprotonated plus protonated. So that accounts for all of it. We plugged in this 0.158, the fraction of our protonated form in for each place that we saw this A minus. And that gave us this formula right here, which when we plugged real values in, we ultimately got to 0.136, which is our equivalence of sodium hydroxide were needed. Once we got that, we took our equivalence of sodium hydroxide and related it to the concentration of our acetic acid, or the amount of acetic acid that was in our mixture. And that's how we ultimately came up with this 2.72 milliliter number for the amount of sodium hydroxide that was added. All right. Well, that's a challenging question. That is a tough question. Everything up until that question, I'm hopeful that you felt a little bit of comfort with. This question itself is one that is a good challenging question because it takes multiple steps. Now, should you expect like 30 of these questions on your exam? No. Is this something that's kind of a reasonable game for an exam? It is, but it's a challenging question. Another way that you could look at this is try to put that in the context of a titration curve, like visualizing a titration curve. What does that look like? What's my x-axis? Concentration of hydroxide equivalents. All right. Well, I hope that was helpful, and I hope you have a great afternoon.